So to understand the concept of potentials, we're first going to need to make sure we understand what a field is. So in high school it was a bit hand-wavy and not very concrete, and honestly not very accurate. So I'm just going to go through a quick example of what a field is so that we can at least get a feel for what we can do with it. So the official definition of a field is that it's an object that for any coordinate and time you give it, it has a value. So for example, temperature would be a field, because if I give you a location somewhere on Earth and I tell you at what time, then you can give me a temperature that point in space was at that time. Same thing with pressure, for example. You can also do the same thing. So if you have a box and you have your X, Y, and your Z components here, this is a cube, I'm just very bad at drawing, then anywhere inside of this, we can define a field. So it can be something a lot more concrete, like for example, temperature, or the electric field is a little bit less concrete, but you can at least directly measure it. Or we can go even more abstract and go to a potential field, which you can't directly measure. We'll go into how that works in the end and what freedom that gives us since we can't directly measure this field. So let's go over to that. So to understand how we can relate the potential field to a force at that point, we need to understand the gradient operator. You might have seen this in the notes, but I'm quickly just going to go over it, and I'm planning to make another video, a couple of videos that go over vector and multivariate calculus, which uses this del symbol, the nabla operator, the nabla symbol and the del operator. It uses it a lot. So if we use it here for a scalar function, I'm just quickly going to, it's just the derivative in the x direction, that should be a y, derivative in the x direction times your unit vector in the x direction plus your derivative in the y direction times your unit vector in the y direction. So this gives you a vector that points in the direction of the maximum ascent, and the length of this vector is related to how fast this function is changing there. So this overall is a vector, and that vector is always going to point in the direction that it's most increasing. So if we take this definition, where the negative gradient of our potential field is the force that a particle will experience at that point, this is a conservative position-dependent force, then we find that the force will always be in the direction, in the opposite direction, since it's a minus, in the opposite direction of the maximum increase, which is the same as the direction of the minimum increase. So, of the maximum decrease, in other words. So if we think about the potential field like a hill, the force is always going to push it down the hill. Same concept. So, because of that, we can directly relate these. But I'm also going to show you how you can go in the other direction, where you can go from a certain force and use the work that you can calculate from this force, that's a field, use a path integral, and then directly get your potential field back from that, since that's the direct inverse of the gradient. So if we consider this field, I just drew some arrows along some diagonals to just give us an idea. If we consider this this field, and we say this is the electric field or something similar, that we know is a conservative field, I'm going to come to one way to test if it's a conservative field, two ways actually. Then, if we assume we already know this is a conservative field, then we can try to set up a potential from this. So we know that the potential is the negative gradient. The negative gradient of the potential is the force at that point. But the inverse of that statement is that we're going to take the integral from one point, say A, to B, and then if we take the work at each point of that infinitesimal segment, that's just going to be the negative potential at B minus the negative potential at A. So that's basically the inverse. So if we expand this a bit, you're just going to get A to B of the force dot your displacement, so we'll call that ds or whatever, and then you're going to get yeah, you can just expand that, that's not really the important part. So if you take this and you want to know, we usually set a reference point. So a custom nice way to do it is to set it at infinity, since then we can just say infinity is 0, and that gives us some nice cancellations. But we can basically take any arbitrary point and set it as our reference point. So I choose this point to be the 0 point. I'm going to define that the potential field at this point is going to be 0. Now, since this is a radial force, we can draw a circle here, and that circle is always going to be perpendicular to these lines, right? So if I move any part of the circle, at each point my force and my displacement is going to be perpendicular. And we know the dot product of two perpendicular vectors is always going to be 0, because that angle between them is 90 and cosine of 90 degrees is 0. So we know that this circle, for example, everywhere on this circle, it's going to be a 0 potential. In the same way, we can always draw contour lines for where the potential is constant. So for a radial force like this, it's always going to be circles. But what we're going to find is if we were to draw force lines here, it's going to go out like this. And that's always going to be perpendicular to the contour lines of your potential field. So that's a nice way to visualize this sometimes. But now, say I don't want to go on a contour line, because that's boring. I want to know what is this contour line's potential. So now I take this point, and then I take any point on this circle. The easiest is going to be there. Now, if I can work out the difference in potential energy there, and I define this point to be 0 energy, that will just give me the potential energy there. And if I have the potential energy here, we already determined that this entire ring is going to have the same potential energy. So the potential energy field here is only dependent on the radius. So it's only how far you are from the point. Exactly the same as our electric field. It has the same symmetries. So that's also an important observation to make. Now we can use our 2 points that are in the same line as our center point, such that our displacement will always be radially inwards, such that the dot product of our force and the displacement when we do the integral is always going to lead to the 2 magnitudes times -1, since cosine of 180 degrees is -1. So if we go through this integral, we just want the force times the displacement. We can take this out of vector form, since we're only going to go on a straight line. We have the minus, since we already determined that. The force's magnitude, which this is just the constant, the normal constant. And the force is going to vary as 1 over r squared, and we're going to go from the radius from point A. We just call point A radius A, just the same thing, since that's the only thing that matters for the potential field, and this point B, which is at radius B. So we're just going to integrate down from there. So we do the integral as usual. Then we notice that we get this UA, which we defined that to be 0. So we can just get rid of that, multiply -1 on both sides, and then we get this expression down here. Now, my camera isn't great, but this is a 1 over A right there. It's 1 over B minus 1 over A. So if we then define our potential field to be 0 only at infinity, then this 1 over A, this A needs to go out to infinity. If we take the limit as A goes to infinity, then -1 over A is just going to go to 0. So then this starts scaling as our normal constant that we always use, the negative of that over B. So if we rename B to just be the radius that we want the potential energy field, it looks a lot like our magnitude of the electric field. Instead of 1 over r squared, we just have a 1 over r, and there's the very important negative sign there, because that's quite important. So that's how that's just an outline of how we usually would calculate something, for example, for a radial force. It can get more complicated, but I doubt they'll make it much more complicated this semester at least. And I'm quickly going to talk about how we can identify conservative fields, because there are 2 ways, and I think both are quite important and can help in different ways. So before you go into the normal calculation of determining whether a field is a force is conservative, I want to give you something that you can watch out for. That's going to at least give you an idea beforehand, so that you can, at the end, when you get an answer, you're probably more certain of your answer, or maybe you need to go look at your calculations again. So we go from the definition of the force as a negative gradient of u. and we've talked about a bit about that. Now, there's a concept in vector calculus that I'm not going to expand on here because it's not necessary, but we call it the curl. And so if we take the curl on both sides of this, we get the curl of this this vector. F is just a vector. The curl of this vector equals the curl of that. And there's a definition in vector calculus that says that the curl of a gradient is always going to be 0. Okay, so that's the important thing. So if our force at any point does not have 0 curl, then we know it cannot be conservative, since we can't draw a potential field for it. Any conservative force, you can calculate the work, so you can calculate a potential field. So potential field and conservative forces go hand in hand. If you have one, you have the other. So what is curl? I want you to imagine a vector field as water flowing, for example. So this is just a normal, say, a stream that flows everywhere in the same direction. If I put a little stick here in the middle, it's not going to rotate at all. It's not going to curl, which is where the name comes from. It's just going to go straight, since all points will have the same force. And since it just goes straight, it means the curl is 0. So this force will have 0 curl, so this force is conservative. The potential field is just 0 because there's no change, but it's conservative. Now for this, say we have this, if you put a stick right here, the stick will start to curl. And since the stick can start to curl, that means that this is not true. The curl of this field is not 0. So we're pretty sure that this will not be a conservative force. It's just to get us started. So if we go to the example that we had in the homework, where you have big vectors and then it gets smaller and then it switches direction in the other side. If you put a stick, it's much more obvious here in the center. If you put a little stick here, it's going to start to spin, because the bottom is going to feel a force in this direction and the top is going to feel a force in this direction. So your stick's going to start to turn. It's going to start to have curl. So this field definitely does not have 0 curl right here. So we're very certain that this field will not be conservative, but we still have to prove it. You can mathematically go through the curl, but we don't do this in this course, so this is just a way to give you an intuition, and that's probably also a bit harder math. So we're going to go to, now that you have the intuition and you have a strong suspicion whether your force is conservative or not, now we're just going to quickly go over an example. I think I'm just going to handle this this example, since it's quite nice and there's a very elegant solution to it. So if we have a vector field like this, ignore the box for now, I'm going to explain that. Then I'm going to quickly outline the approach. There are 2 equivalent ways of looking at this. You're always going to want to have 2 paths that go to the same point. So if we take this as our starting point and this is our end point, then we can consider what will be the work that's going to be done by this force if we go straight there. So we're going to define it in some way that it's going to cancel out nicely. So for example here, it's always, your displacement's always perpendicular to your force, so the work down this side is just going to be 0. Same for down this side. But now, if we go in this direction, we're going to see that this is always in the opposite direction, but it's not perpendicular. So we're going to have negative work the entire way here. Now, by the same logic right here, it's always going to be in the opposite direction of this, but it's never going to be perpendicular, so this will have total negative work. So if we sum this, and this side, it's going to be a negative plus 0 plus a negative, so that's a bigger negative number, and that's not the same as this number, which is 0. So our work going from here from our start to our end by this path is not the same as our work that's going to be from here to here by another path. So that means the work done by the force is path dependent. So that's one of the ways of determining that the force is not conservative, and that's one of the best ways to prove it. And another equivalent way is to not have a start and an end point, but have them on the same point. So we're going to make a loop. So a conservative force, if you make a loop, the total work is going to be 0. But by the same argument, if we go down here, it's a negative number, then we take the work from down this side, which is going to be 0, then another negative number, so we have a bigger negative number, and then we go back up here and it's 0 again. So if we have a negative number plus 0 plus a negative number plus 0, that's not going to be 0. and we just made a loop in a field, in a position-dependent force. We made a loop, and the total work done by that force wasn't zero. So, since the total work done isn't zero, then we know that this force can't be conservative. And this aligns with our intuition from previously, where because if we put a stick here and it's going to start curling, that means that the curl isn't zero, so this is probably not a conservative force. We see that if we go through the motions, you can do this mathematically as well, if you have a definition for the force, then if we go through the motions, we see that indeed it is not a conservative force. So that's the main way that you're going to determine whether or not something is a conservative force.